In this video, we're going to explore the synthesis of epoxides from alcohols, a common starting material for a lot of syntheses, and the opening of the epoxides that we create. The only way we know how to make epoxides is from alkenes, and that's not going to change for the whole semester. So, big hint. I believe we're making alkenes in the first step. When you see a combination of an alcohol with a strong acid that's either toluene sulfonic acid or sulfuric acid, you should be thinking about dehydration of alcohols, found in Chapter 10. Major product will be the most substituted alkene. In this case, a tri-substituted alkene. It's got 3 carbons attached. 1, 2, 3. This would be the less substituted alkene, di-substituted. 1, 2. What happened to our stereocenter up here? Well, it's sp2 now, not a stereocenter, it's flat. We didn't react this carbon here, so it stayed the same. This is a per acid called metachloroperbenzoic acid. It's found in Chapter 11, and percarboxylic acids form epoxides. Here's an epoxide. We'd get a 50-50 mixture of this one and the other one that would look like this. Dash, dash. We don't need both, just one. We're going to explore the various ways to open this epoxide on the bottom of this page because it has different substitutions on each carbon. A more substituted carbon favors cations. A less substituted carbon favors attack by strong or medium nucleophiles. All of this in due time. Another way to make epoxides is to do a vicinal halohydrin formation. That's bromine in water. And then do an acid-base reaction, which will be followed by a neighboring group participation. And I just noticed here we had this little shadow here waiting to be unveiled. We never talked about the other product in an acid-catalyzed dehydration. That would be water. Okay, so we're going to get an epoxide here, and it's an enantiomer. I went with the dash dash on this one. The enantiomer would be, oh, poor choice of words. Not an enantiomer. Diastereomer. What I'm about to draw is the diastereomer of what's already drawn. This stereocenter stays the same. This one's different. This one's different. 2 out of 3 changed, not all 3. Those are not enantiomers. This is the diastereomer of the thing that was here before, which is right there. Okay. We're going to do the ring opening of the epoxides now. Forgot to shadow this one. This acid-catalyzed opening of epoxides found in 11.5 creates a vicinal diol. This is a different way to do it. And the nucleophilic opening of epoxides with a strong nucleophile like hydroxide gives the same result. Reason being is we have the same substitution pattern on both parts of our epoxide. And I guess I kind of explained what diastereomer meant. What is meant by diast. 2 diastereomers. Here, let's have them both shown here. These are identical molecules right now. Let's draw the other isomer formed in the top one and then compare it with the bottom one. You always have anti-results from triangles. You remember that. Okay, so these 2 are diastereomers. Top stereocenter is the same, and this one's different, and this one's different. Some changed, but not all. That's diastereomers. Okay. I'm going to spend the rest of the video doing lots of good things with this epoxide here. Here are 4 reactions of our epoxide. In this one we have acetylide, an old friend from Chapter 7. That's a strong nucleophile. It's going to react before we add HCl. That's what 1 and 2 means. Here, this is going to react, and then something's going to happen. I think I'm going to change the color of the H to green, because that's where the H comes from. H is one of those. Clearly nitrogen lost an H. In this one, very similar to the very first one, identical actually, except different strong nucleophile does the attack first, and HCl protonates the O. Here, these are not the same at all. Not the same at all. This is all together. We have ethanol with HCl dissolved in it. Before any reaction can happen, this poor nucleophile has to wait for the carbons to become more reactive. HCl accomplishes that task. So let's get all of our nucleophiles drawn out so we can use them in mechanisms. Strong mechanism, strong nucleophile, moderate nucleophile, strong nucleophile. They both behave the same, those two types. They attack the least hindered carbon and pop open the epoxide in this fashion. Less hindered is on the bottom for each one of these, and we pop it open here. Same story for all of the other ones. Gets popped open after the attack by the nucleophile. I'm just doing this for expedience. This one's not getting popped open right away. The attacker is always the same kind of thing. Backside attack on the triangle, backside attack on the triangle. So the three intermediates we're going to form there are here. So in our first step is the attack using a strong nucleophile or a moderate nucleophile. We generate the same kind of intermediate each time, these three intermediates, and they are the conjugate base of the final product, and that is the end of step 1 here and the end of step 1 here. Step 2 separate. HCl has to be added separate so it doesn't destroy the nucleophile you just used before the thing even starts. And HCl is used to protonate our intermediate, to get to our final product. Same story over here. HCl is going to protonate, and Cl minus is liberated. And down here we have a slightly different story. There's no HCl around before or after the first step. O minus is the conjugate base of an alcohol. The product will have a pKa of 17. The reactant here has a pKa of 10. We can't even stop this from happening. 10 always goes towards 17 in an acid-base reaction. This is just an intramolecular acid-base reaction, giving us our final product. And there you have it. All that remains is for us to explore this fourth one and give our descriptions and reasoning. In our final one, we don't have a strong nucleophile or a moderate nucleophile. Ethanol is a poor nucleophile. It will not touch an epoxide. We have to first activate our epoxide by protonating it. Activating it means make it more reactive. This is going to create an oxonium. We'll show the oxonium here. This oxonium is activated towards attack. It's also a cation. The oxygen has the cation here, and the carbons are doing their best to help with the cation. The question now is, which of the carbons would be a better cation, because that's the one that's going to spend more time with a plus charge. This is not about the nucleophile coming in and attacking the least hindered carbon, which we will see in our reasoning for these three. It's about which carbon spends more time with a positive charge. I did not concern myself with that for any of the first three because I did not see a positive charge. So I'm going to go for the carbon that spends more time with a positive charge. This looks more like our first study of triangles, doesn't it? Backside attack on the more substituted carbon. Oxygen gets neutralized. We're going to get another oxonium intermediate right here. This oxonium is the conjugate acid of the final product. You could use ethanol, the solvent, to pick up this proton, or chloride. I already have chloride drawn here, might as well use it. And it's going to grab that H. My arrow went off the page, I'll fix that. So this generates our product here that has the nucleophile on the more substituted carbon. Of the 4 products, this is the only one where that's the scenario, that's the case. Our explanations for why we observe regioselectivity and stereoselectivity. Step 1, the strong nucleophile attacks the least hindered carbon. That's why it ends up down here. Down here. And it's a backside attack, which gives anti. There's no step 1 down here. The moderate nucleophile attacks the least hindered carbon from the backside to give anti-stereoselectivity. And this will be identical to the first reaction's explanation. And over here, we're almost there. We activated the epoxide first with a strong acid. We couldn't do that in any of the previous examples. There was no strong acid in step 1, no strong acid here, no strong acid here in step 1. Here we have strong acid available from the beginning. That's what you do when you have a strong acid available. You protonate something. And then the poor nucleophile, which was otherwise uninterested in attacking an epoxide, the poor nucleophile attacks the more stable carbocation. That's the secret here. Once you get to cations, which of those 2 carbons is the better cation? It's that one. This one's less hyperconjugated. And that is the end of the story. So we have all kinds of ways of opening epoxides. We create great functional groups like ethers that have alcohols. This is the opposite regioselectivity of the one above, ether and alcohol, and reversed regioselectivity. Here we get an amine with an alcohol in the same molecule, and here we get an alkyne with an alcohol next door. Very useful functional groups. Epoxides are very useful for synthesis. That's why we spent so much time with them. I hope you found this video on the synthesis of epoxides from alcohols and their opening to be useful, and look forward to seeing you use them on test 4.